Make sense? So that's how we find the total resistance of the series. Now, or the circuit. Why do we want the total resistance of the circuit? Because guess what I'm going to be asking you to do in the very near future? To determine the current in the circuit. So let's back up. Start easy. If we come back to this series branch, if I said find the current, let's do it through the battery, how would you do that?
9 divided by 400.
Excellent. V equals IR. Therefore, I equals V divided by R, which in this case, we have a 9-volt battery. That's the only guy pushing, right? There's not more than one battery. Divided by the resistance of the whole circuit is 400. And I get, that's 9 400s. 0.025, maybe 0.0225. So we'll call it 0.02 amps. Is the circuit, the current through the battery. Now, what though is the current through the first 200 ohm resistor?
Divided by 200?
Good guess, but no. Who's going fastest if we're all on Park trying to get over to Central Expressway and everybody's going as fast as they possibly can? Who's going fastest? The car that's at Coit or the car that's at Independence, if there's no stoplights and we're all trying to get there going as fast as we can?
Independence. Not going faster, you just I think.
Okay, who's going faster?
The person at Independence. Well, none of them going faster. If they're all going as fast as they can, let's just put them.
Right. When you're waiting in line, who's going fastest in line? The person who's second in line or 40th in line? They're all going the same, right? If you're in the same line, you're going the same speed in that line. Right. That's what's true in circuits. In series, the current is always constant. Yes, I couldn't have made that a more dramatic pause and emphasis, could I? In series, the current is always constant.
How would it not be constant? Like, what would it be? Besides being constant, would it change?
Bless you.
We don't bring in ifs into science.
Well, I'm just having a hard time wrapping my brain around the question. If it's always constant, what would it be if it wasn't constant?
Yeah, how is it not constant? Is there a time where it's not constant?
No.
So it's just the answer you get from the formula?
Well, no, it's just, okay. Here's another analogy I like to use besides the park analogy, and we'll develop this even more next year. It's the playground analogy.
Are you saying the current knowledge to be no matter where you are in the circuit?
As long as you're connected in series, yes, the current's the same.
But if it's in parallel, the current's different.
Absolutely.
All right, that was it.
Okay, yeah. Sorry. Yeah, in series it's always the same,
Okay.
and it's always constant for that voltage and resistance.
Yeah.
Okay. Now, let's come over here, and so I'm sorry, let me finish that out. So what's the current through the 200 ohm resistor? 0.02. What's the current through the other 200 ohm resistor? 0.02. So the current's the same in series, always. Now let's go over to this parallel branch. What's the current through the battery?
Current through the battery?
Mm-hmm.
We have a zero resistance, right?
Ah, good question.
What, I mean, you haven't reached the resistors yet, have you?
Yes. Okay, not yet. Well, here's the deal, right? You haven't gone through the resistors, but you're in line for the resistors. And what do we just say? If you're in line for something, you're going to say speed.
So does through the battery mean overall through the whole circuit?
Yes. The reason we just found the total resistance is because that's what's connected in series with the battery. And so if we find the total resistance of the circuit, we can find the current through the battery, because everybody in the battery's waiting in line to go through the circuit. So yes, I used the 9 volts from the battery divided by the total resistance of the circuit, which in this case was 100, to get 0.09 amps.
Oh, I get
So the current through the battery is 0.09 amps. Now, what's the current through this 200 ohm resistor? Is it A, 0.09 amps, B, less than 0.09 amps, or C, greater than 0.09 amps, or D, cannot be determined? Do you know sign language? A, B, C, D? A is 0.09, A, 0.09, B, less than 0.09, C, greater than 0.09, D, cannot be determined. Cannot be determined. All right, where are my A's? Oh, okay. So you're saying it clearly can't be equal to 0.09 because they're not in series. Good. Where are my B's? There's just a couple of B's. Thank you. I see that hand. C's. 1.5 C's. And D's. And a few that just absolutely didn't commit at all. Thanks for playing. Thanks for not playing. Well, let's think about it. Here's the total traffic going Bush and Park. Here's Bush, here's Park. Anybody want to change their answer? Where are the A's now? Where are the B's now? C's? Come on, D's. Alright, yeah, it's B. Less than 0.09. Because if the total current in the battery is 0.09, and then you get to right here, you got two choices, right? You can go this way, or you can go that way. So can there be equal to or more people going each direction than there are total people? No.
That's impossible.
So it has to be less. Now,
There are only so many people going through.
exactly. Now tell me, we got it down to less than 0.09. Who wants to give me a number? 0.018? 0.045?
I would guess it was
1 over E? Throwing out options. Yes. 0.045. How did you know it was half?
Oh, okay. I didn't want to know.
That would be the resistance for that individual.
Yes. Careful though, because it only works because this is such a simple circuit. We'll get there though. What now?
That makes sense because when we put the light bulbs in parallel, the light bulbs dimmed by half. They dimmed by half. They had half the current going through them.
They did?
Yeah.
In parallel or
In parallel. They were supposed to do that, aren't they? Like compared to when they were lit up just one light bulb?
Let's talk about it. Let's take a 200 ohm resistor and connect it to a 9 volt battery. What would the current in that be?
0.9. No. 9 divided by 2. Which is...
If I took one bulb and connected it to one battery, I have 0.045. So if I take one bulb and connect it in series to the battery, and then I take two bulbs and I connect them in parallel to the battery, which is brighter, the one bulb alone or the two bulbs in parallel? They're the same because they have the same current. Now, but which was brighter when you connected the two bulbs in series or the two bulbs in parallel? Parallel, because there's more current flowing through them in parallel. There was 0.02 amps when they were in series. There's 0.045 amps when they're in parallel. So it will brighten as I connect them in parallel instead of in series. Yes?
Does that mean that you can line up these voltages you want for battery if you have them all in parallel?
Good question, yeah. So can you light 1,000 bulbs with a single battery if you connect them in parallel?
I think you reach a certain point where you
It'll be whatever your bulbs run out. Too much resistance your bulbs.
What's that?
They should run out.
Yeah, you're going to run your battery down. But you're right. You're going to light that many bulbs. It's just the battery's going to drain really quickly because the total current...
More current flowing through?
Right. The total current out of the battery gets larger each time you add a bulb.
I like 100.
So it drains it faster. Right. Okay? Now, right now we need to learn what's called Kirchhoff's
No, German.
Swedish.
Junction Rule. Yes. Kirchhoff's Junction Rule. And it's real simple. At any junction, the current in has to equal the current out. So here's a junction right here, right? That's a junction. At that junction, the current in has to equal the current out. So this current in was 0.09, and you got two choices. Now, is it always going to split up half one way, half the other? It's going to depend on, well, I mean, at a junction where there's one in and two out. Good, it depends on the resistors. If those two resistors have the same resistance, then we're going to split up half and half. But if one resistor is larger than the other, then will there be more current going through that branch or less?
More towards less resistance.
Good. More current towards less resistance. So wherever the branch with the larger resistance is going to have less current. And it's going to be in a ratio of the resistors, yes. So in this case, same resistance, and so it's a 1-to-1 ratio. But if one of these were double, then you'd have twice as much current going through the one with half the resistance.
So are you going to make us do an
No, we're getting it, yeah. Okay? So what's the resistance through, the current through this? 0.045. And those two have to add up to 0.09. And they do. Now, When the current goes through that bulb, what does the bulb do?
What's up?
It lights up. The reason it lights up is because when it lights up, it's giving off heat and light, energy. Where did that energy come from? The electricity. So the current, as it goes through the circuit, and this is where it gets a little tricky, the current doesn't slow down. In other words, what's the current right here, right before we get back to the battery? Still 0.09. We're still in line, we're still in series, we're still going the same speed. But it loses energy. So as I go through the circuit, I don't lose speed, I don't lose current, but I do lose energy. So what happens to me is I start off at this side and I have a lot of energy because I'm on the positive terminal of the battery. I want to get out of here. So I take off around the circuit. No matter which way I choose, I go through a resistor. And as I go through a resistor, I heat the resistor up, which causes the resistor to gain energy and for me to lose energy. And so my energy drops until I get back to here. And then if I could go through the battery, since it's direct current, it doesn't go from the negative to the positive. But if I could, what would happen to my energy? Go back up, right? I get re-energized. How much would I get re-energized as I went from the negative terminal to the positive terminal of the battery? 9 volts. So, how much is my energy dropping as I go across that bulb? 9 volts. Let's check that out.
How do you know it's exactly 9 volts? What if they're multiple resistors? Is it
Okay.
time to drop 9 volts?
We're getting there. We're getting there. Let me ask that. How do I know? Well, first of all, I can use Ohm's law, right? Do I know the current through this resistor? 0.045. Do I know the resistance of this resistor? 200. If I do V equals IR, guess what V equals? 9 volts. So how much did the energy, right, or not the energy, but the voltage drop as I went across that resistor? 9 volts. See how if I go around this circle, this loop, my energy raises 9 volts and then it drops 9 volts. Raises 9 volts, drops 9 volts. So that every time I pass any given point in the circuit, I have the same amount of electric potential.
Wait, so how does it, so you're saying it goes down to 0 volts at one time?
Well, here's where it gets tricky,
So
right?
How does it move?
Voltage is relative. Like potential energy is always relative. It's always relative from one place to another. And so if I call this point 0 volts, then yes, it gets back down to 0. Now that just means it doesn't have this stored electrical energy in it. And we're kind of getting beyond, we're having to oversimplify a little bit. But if you think of, I think your question was how does it get back, right? Remember, it's not slowing down. The current's the same. It's just losing energy.
Oh, so
Think of it this way. Think of the electrical current as being a flow of water. Where the current, at the rate at which it flows, doesn't depend on how much energy the water has. For example, let's say we have really hot water. Can that hot water heat something up? Yes. So it can transfer that energy to something else to warm it up without slowing down. So when the water returns back to the battery, it's cold water now, but it's still moving just as fast as it was when it left. So if I have a water pump in my car, right, starts off cold, gets heated up by the radiator comes back hot, and then I cool it off again. The temperature, the energy content of the water is changing, even though the flow rate, which in this case is the current, doesn't. All right? Now let's look at the series example. Now I leave the battery. I've got 9 volts that I didn't have on the negative terminal. How many resistors do I have to go through? 2. How much is my voltage going to drop across the first resistor? Half. How do I know it's half? Because I've got to have half left to go through the other 200 ohm resistor.
How does the parent know ahead of time that there's a resistor?
It doesn't. Good question. So I'm going to use Ohm's law to determine the voltage drop. What's the current through this resistor? 0.02 amps. And what's the resistance of this resistor? 200 ohms. Actually, it was 225, wasn't it? I rounded too much. So what's the voltage drop across this resistor? 200 times 0.0225, which is 4.5 volts. And then that same current goes through the second resistor and drops another 4.5 volts.
So is it that every time the current leaves the 9 volt battery and when it returns, it'll have, if it's going through the resistor, it'll have a 0?
Right. It will always return to the same point relative to where it started. Yes. So if it started 9 volts high on the high end, then it's going to return at 0 relative to that 9 volts. Okay? And that's what we call, we had Kirchhoff's junction rule. This is what we call Kirchhoff's loop rule. And Kirchhoff's loop rule says that in any closed loop, the voltage rises have to equal the voltage drops. So in this case, this red circle, we went over a voltage rise of how much? 9 volts. And then we came down through this resistor and we had a drop of 9 volts. What if we had gone through this resistor? We have a voltage rise of 9 volts. What's this voltage drop going to be? 9 volts.
Because the energy from the first one that dropped 9 volts hasn't passed through them, it's new energy.
Exactly. And these guys, at these 2 points, no matter which path I take, I have to end up with the same energy. Because I can't have 2 charges at the same location in the circuit with different amounts of energy. Alright? So I come over here, I've got a rise of 9.5, a drop of 4.5, and then another drop of 4.5, so my total rises equals my total drops. Alright, let's move on to a little more complicated one. What's the current through the battery here? Oh, first I just got to tell you what the voltage of the battery is, right? Sure, we'll make it a 9 volt battery. It's who?
9/850th.
Yes. 9/850th, which is 0.011. And by the way, we're going to round responsibly, right? Keep 2 or 3 sig figs. But just know that because of the rounding, there's going to be times when two numbers should be exactly equal and they're going to be off by a little bit. So just be okay with that. Who? Oh, yeah. Since we have the total resistance we found earlier was 850, right? And so V equals IR. Therefore, I equals V over R. And the voltage rise for the circuit is 9 volts because that's the only battery connected. And the total resistance was 850. So 9 divided by 850, 0.011 amps. So that's the current through the battery. But what on earth is the current through the 300 ohm resistor? What? 0.011? Why? Good, because in series, the current is constant. Therefore, the current through the 300 ohm resistor is
Even at the end of the 300 ohm resistor?
0.011. Throughout.
But it just went through 300 ohms of resistance.
Exactly. And so what happened to it?
Lost energy.
It lost energy, but it didn't slow down. Right? Think of the water. The flow rate stays the same even if the temperature of the water changes. But clearly, when it gets over to the 400 ohm resistor, the current's now 0.011.
So what about within the...
So 1 to 3 ratio.
All right, so now let's get to this parallel branch. Because the current clearly is going to be 0.011 through the 200 ohm resistor, right?
0.0027.
No, because if all the current was going through the 200 ohm resistor, then the 600 ohm resistor would get lonely. So, it's going to split in a ratio of 1 to 3, where there's going to be 1 here and 3 there. So I could, how many parts do I need? 4. So I could take my 0.011 and divide it into 4 parts. And what do I get when I do who? For the 0.00 what? 2 8 come back.
We don't want to do it this way. 4, 11, 4,000.
I'm trying to find. We're doing the first one first, right? So one part goes this way. So this current is 0.0028. And then the other 3 parts go to this side, which is 3 times that. Right? 0.0 who? 0.083.
I'm going by 0.028.
Or 8384. Okay. Now, if I add those two together, oh my gosh, I get 0.011. By which rule? That's the junction rule. Because here's a junction that says that the current's going out, which is this case is 0.0028 and 0.083. Oh wait, I lost the 0, didn't I? No, that's right. Right? Did I do that right? Yeah, I lost the 0. 0.0083. When I add those two together, I get 0.011. Which I better. Because the guys coming in have to equal the guys going out. Fair enough? Now, what's the voltage drop across the 300 ohm resistor? How much voltage did I lose by going through that 300 ohm? 3.3 volts. How much did I lose going through the 400 ohm resistor? Take the current times the resistance, right? 4.4, right? Current times resistance. Current times resistance. So how much is left to drop going through either the 200 ohm resistor or the 600 ohm resistor? So far, when I take the 300 and the 400 ohm resistors, I've dropped how much?
7.7.
7.7. So how much left do I have to drop?
1.3.
1.3, because my 9 volt rise has to be erased by all 3 drops. So I already know that there's a 1.3 drop across the 200 ohm resistor, and there's a 1.3 drop across the 600 ohm resistor. Should that be true? Should those two voltages be the same? By the loop rule. Right? These have to be the same voltages. Alright. So then, yes. Voltage drop here is 1.3. And again, I can do it by IR too, right? Since I already have the current. 0.0028 times 600 will be 1.3 volts. And 0.0083 times 200 will be about 1.3 volts. So that either path I take, whether I go this way or this way, oh, I already have that color, or this way, either one of those two paths, if I add up all the rises and all the drops, they have to be equal. So take the yellow path. Drop of 3.3, drop of 1.3, drop of 4.4 equals a total of 9 volts of drops and then a 9 volt rise. If I do the same thing for the green path, drop of 3.3, drop of 1.3, drop of 4.4, that's 9 volts of drops equals 9 volts of rise.
So because it's a battery, does it actually a rise in voltage, or does it just start high?
Right. Because it's a battery, it doesn't actually pass through it, and so it's not going to actually rise, but as far as the circuit's concerned, yes, from one side to the other is a rise. Even though the charges themselves don't pass from one terminal to the other. Okay? All right. Do this one on your own, please. Find the current through the battery and all 4 resistors.